Types of symmetry elements and operations, part 2. I'm again your instructor, Saurav Muktibodh. In the earlier section, we have studied identity, number 1, number 2, center of symmetry, and number 3, mirror proper rotation or axis of rotation. Now, 2 more operations are left with this. They are mirror planes and improper rotation. Mirror planes and improper rotation are left now. So let us discuss them one by one. We'll start using the mirror planes or the plane of symmetry. You notice this butterfly. Beautiful, isn't it? But if you can notice this, that this butterfly can be divided into equal halves by inserting plane into it. And this plane is going to divide this butterfly into equal halves. Similarly, if you choose a water molecule and insert a plane like this, it is going to divide each atom into equal halves. And not only this, this plane is going to divide oxygen atom so that the hydrogen atoms get exchanged and the configuration still remains superimposable. So the plane that the water molecule is containing right now is vertical plane of reflection, and this bisects the molecule into equal halves. As you know that this is demonstrated, that is signified, that is symbolized by sigma. If we perform the same operation one or more times, then what happens? Sigma 1 is sigma, of course, but sigma 2, if we are doing the same thing again, that is going to result identity. And if we continue doing so, again sigma 3 results in sigma, sigma 4 results in identity, and so on. So sigma n remains sigma if n happens to be odd, and it becomes E if n is even. So strictly speaking, that sigma does not generate any operation, as we have seen in case of proper rotation. If we want to classify the types of mirror planes, they have been generally classified into 3 types. Number 1 is the vertical plane of reflection, that is denoted by sigma v, horizontal plane of reflection denoted by sigma h, and the third one, that is dihedral plane of reflection, that is denoted by sigma d. Let us try to understand them one by one. We take this example of water molecule. We have demonstrated C2 axis here, and one more plane, that is sigma v dash, is in your perusal. What we notice? Should it be in a horizontal plane of reflection? No. It is just not in horizontal plane of reflection because the principal axis C2 is not perpendicular to it. It is in fact collinear with the principal axis. So all those planes which are collinear with the principal axis are termed as the vertical plane of reflection. You just notice the subscript V, sigma V and sigma V dash, both are the vertical planes because they are collinear with the principal axis. They are not perpendicular to the principal axis. The horizontal plane is very obvious, such as one in benzene. If we insert a plane in benzene, all carbon and hydrogen atoms would be divided into equal halves, and this is perpendicular to the principal axis C6 as shown here. So generally, such kind of planes are also known as molecular planes, and they are perpendicular to the principal axis designated by sigma h. The third one is the case with the dihedral plane of reflection. This is the plane which bisects the bonds, and it is said that it passes between two mutually perpendicular C2 axes. Just take the example of xenon tetrafluoride molecule here, and we can see that apart from having the xenon fluorine planes, we have a plane that only takes xenon into account and reflects rest of fluorine atoms. So this plane is typically known as the dihedral plane of reflection. Just notice the another planes in this molecule. The vertical planes, though they are collinear with the principal axis, but they are containing as many bonds they can. For example, here xenon-fluorine, xenon or fluorine-xenon-fluorine planes are contained in both the cases. However, in this case, where we are discussing about the dihedral plane, it is passing through the C4 axis, which is perpendicular, it is passing through the axis which has it is passing through the xenon atom only that are not containing any fluorine atoms. So the two typical structures here, sigma d and sigma d dash planes, they are only taking xenon into account, reflecting the rest of the fluorine atom as they have been indicated. Also, because the molecule is flat, it would also have a horizontal plane of reflection which is perpendicular to the plane, or rather it is perpendicular to the principal axis. Next thing that we are going to talk about is the improper rotation. An improper rotation is actually the combination of two independent symmetry operations. They are rotation and reflection. And therefore, what we generally say is Cn followed by sigma, that is rotation followed by reflection, is an improper rotation. Cn into sigma or sigma into Cn. So we also call them as a rotation reflection symmetry, rotational reflection axis as well. The essential requirement and that most important requirement for this operation to exist is Cn must be perpendicular to the sigma. It should be noted that the S1 does not exist because S1, if it would have been existing, it must be a product of C11 and sigma 11, and C11 is nothing but identity. So what you are left with E and sigma 1, that is sigma. So S1 is as good as sigma. So it does not have any separate existence, as you can see even in this figure, where you have only the reflection operation is taking place while C11 is nothing but a complete rotation by 360 degrees. In the similar lines, S2 does not exist, and what exists is center of symmetry I. Just now you notice here that if you perform S2, that means you are performing a C2 rotation by 180 degree followed by reflection to the plane perpendicular to it. So remember that S2 does not have any independent existence and only I does exist. It's quite interesting to understand the improper rotation for methane molecule, and it can also be demonstrated that the two operations commute. That is, it does not matter whether you perform a C4 first or sigma first, the end product is always the same. So C4 into sigma is equal to sigma into C4, and that is collectively known as S4. That we can demonstrate by use the example of this methane molecule, which is tetrahedral. We can see that they have been labeled, hydrogen have been labeled as HA, HB, HC and HD, and the two hydrogens are now mutually perpendicular to each other. Just notice in the structure, and if we rotate this molecule by 90 degree, that is, if we perform a C4-1 rotation through the axis that has been shown, you find that the positions of these hydrogens have been changed. HB has been changed to a new position where there was no atom previously. Similarly, HA has occupied the place after the plane, and the lower hydrogen atoms have also been changing their places. For example, HC has moved to this frontal position while HD has occupied the back position. Notice that if we are performing this operation, C4-1 operation, the two structures are not identical structures. They are not superimposable structures, and therefore C4-1 is not an operation by itself. However, if I perform a plane perpendicular to this axis, and I will see that the atoms from the top are exchanged to the bottoms. So C and D from the bottom goes to the top position, and B and A also are getting exchanged. So that is the structure that we have received after two operations, that is rotation and reflection. Now we are getting the new configuration that is superimposable to the first one, and it means that though hydrogens are not exactly same, but this operation has been considered as a new operation, is a combination of two independent symmetry operations. Similarly, if we start with the reflection first, just see the reflection plane inserted in a cube, and if we do it, we'll find the elements from the top would move to the bottom, and if we now rotate it, you get the same thing. Just notice. So sigma independently does not exist. After rotating by 90 degrees or applying a C4 operation, we get exactly the same thing as we have seen earlier case. So I can conclusively say that S4 which is a combination of C4 into sigma, is always sigma into C4. That is, the two operations always commute. Note that similar to the proper rotation, the improper rotation also generates S binomial operations. For example, if we say that there is an S4 axis, then it is expectedly generating S41, S42, S43 and S44. S41 is S41 itself, but S42 can be decomposed as C42 into sigma 2. Now C42, that means it is C2, that is Rotation by 40 degree twice is as good as rotation by 180 degree once. So C2 and sigma 2 is E. We have learned that if n is even, we get identity. So S42 is equivalent to C2 and therefore it does not exist separately. S43 can be changed, so it remains S43, and S44 is obviously going to be identity. So S4 axis generates two genuine S4 operations. They are S41 and S43 respectively. The staggered conformation of ethane has an S6 axis that goes through both the carbon atoms. That you can see, you are just applying first a rotation of the 6th degree and then performing a reflection plane so that the resulting operation gives an S6 axis. This S6 axis would generate again 6 operations: S61, S62, S63, S64, S65, S66. S61 remains S61. S62 becomes as twice sigma twice C6. So twice sigma becomes identity. C6 once and C6 once makes C62. That remains equivalent to C31. So S62 is as good as C31. Similarly, S63, that is thrice sigma, thrice C6. Thrice sigma makes 1 sigma, because 2 sigma is identity, remains what left is sigma H, and the rest of the 3 6 makes C63, that is equivalent to C2. So rotation by 60 degree thrice is as good as rotation by 180 degree once. Now remember that this combination, that sigma H into C2, is nothing but S2, and as I told you that S2 is equivalent to I. So even then S63 does not exist. Similarly, if we talk about S64, that goes to equivalent to C32, S65 remains S65, and S66 goes to E. So an S6 axis is actually generating two genuine symmetry operations. They are S61 and S65. Others are manifested in different terms, so they are not considered separately. Sequence of operation generated by S6 are S61, C31, I, C32, S65, and identity. Now you may be, as an example, asked to identify all the symmetry operations and elements and operations for different molecules, because now so far we have discussed all the types of symmetry elements and operations that a molecule may or may not have. For example, if we take the simplest example, this water molecule, it has 4 symmetry operations as E, C2, sigma B, and sigma B dash that we have described earlier. And similarly, the ammonia, another pyramidal molecule, that is quite simple case study, that is identity. It does have a C31, C32, and 3 independent plane of reflections which passes through nitrogen and hydrogen atoms. Similarly, if we wish to identify all the symmetry operations for boron trifluoride flat molecule, we'll of course say that identity C3 axis that generates C31 and C32. C2 axis, there are 3 C2 axes, one along BF1 bond, another along BF2, and the third one along BF3 bond. So there are 3 C2s which are perpendicular to principal C3 axis, and the 3 vertical planes, sigma V, BF1 bond, sigma V dash along BF2 bond, sigma V double dash along BF3 bond, and because the molecule is flat, it has a molecular plane which is perpendicular to the principal axis. But that's not the all. What does it have is also improper rotation S31 and S32. So that makes a total of about 12 symmetry operations that are existing in this molecule. So to sum up, I would say the symmetry elements and operations are two slightly different terms but are often treated collectively. A symmetry operation produces a superimposable configuration. There are 5 fundamental symmetry operations. They are identity, proper rotation, mirror symmetry, center of symmetry, and improper rotation. Okay. A molecule may or may not contain all symmetry elements and operations. More operations present assure more symmetry. So once we identify all the properties of symmetry properties of the molecule, we can go for identification of molecular point group. And once we do it, our complete detailed applications of group theory are open to be explored. Thanks for watching this video.